First of all, let me thank a lot the organizers for the great opportunity they gave me to speak here today. It's really a great pleasure. My name is Ippocratis. I come from Prague, and I will be telling you about works I have been doing over the years, and also some ongoing work together with Luca Mentola, Martin Kunz, Ilidio Lopez, Maria Limota, and Ignacy Savitsky. Okay, right. So I would like to summarize the motivation for the talk in three simple questions. The first is, how much can we learn about the acceleration of the universe in a way that is model independent? And what I mean by that is in a way that does not assume any particular parameterization about the dark sector. This means any particular parameterization about either dark energy or dark matter, or assuming any particular model of gravity. Now, the second question is, what can we learn from gravitational waves, the propagation of gravitational waves at any scale, either cosmological or astrophysical, and what we can learn from them about the large-scale structure of the universe. This might sound somewhat counterintuitive in the sense that gravitational waves probe spin-2 fluctuations, while the large-scale structure of the universe is caused by scalar fluctuations. As I'm going to argue, there is a direct link between the two, and we can extract information about the properties of the physics of the large-scale structure physics of the universe. And finally, I will close with some recent constraints coming from stellar structure and how these connect with the properties of the theory at cosmological scales. Right. So I think it's fair to say that we do have a model that works very well at the phenomenological level, modulo the current tensions, which are very important. And this is lambda CDM. The problem here is that we cannot explain the cosmological vacuum. And this is a severe theoretical problem. It's a problem of naturalness. The infrared value that we tune for the cosmological constant is highly sensitive to the UV initial conditions. And this is a big problem. Modified gravity models, which I will be introducing in a bit, sometimes try to attack the problem directly through some vacuum screening mechanism, or they somehow leave it on the side and try to explain the acceleration of the universe in a dynamical way. Whatever the case, though, it is important to test the effective gravitational interactions between different degrees of freedom at both cosmological and astrophysical scales. And with a wealth of current observations, we have a great chance to do so. So now let me introduce the models I will be talking about, which I classify conveniently for the purpose of my talk into three distinct categories. So I'm starting from general relativity, and I'm considering an introduction of a new scalar degree of freedom, a new theories that introduce a new vector and a new tensor degree of freedom. Now, the first category is probably the most popular one, the most well-studied one. It starts from the archetypal branch-Dicke theories, which couple curvature to a scalar through a conformal coupling. Their generalization to Hordensky theories, which are the most general theories one can construct from the metric and the scalar that gives a second-order equations of motion, and the more recently introduced the beyond Hordensky theories and the degenerate higher-order scalar tensor theories. Now, vector theories are more tricky because we have to ensure that the cosmological isotropy is preserved. And here we have the relatively old Einstein ether theory, the particular limit of Horzava-Lifshitz gravity, and the recently introduced generalized Broca theories. Now, introducing a tensor field, a new tensor field that interacts with the standard graviton, is going to break diffeomorphism invariance. the graviton picks up a mass, and we're talking about massive gravity or the more general bimetric gravity and their generalizations. Now, it is important to point out that all these theories have some distinct phenomenological, generic phenomenological imprints at different scales. For example, in principle, they modify the strength of gravity at large scales, and they achieve this by modifying Newton's G in a way that it becomes a scale and time-dependent constant. This has as an effect the change of the strength of clustering of matter at large scales. We introduce a gravitational slip in principle, which is a difference between the magnitude of the two scalar potentials at linear scales, phi and psi. As I'm going to argue later on, the gravitational slip is a key discriminator between large classes of models. And because geometry is modified, these theories introduce a modification to the weak lensing effect. And usually the parameter to describe, to quantify this is this sigma parameter composed by the eta and the G effective parameter respectively. So sigma is equal to 1 GR and conformally coupled models, but it's different from one in principle from models that couple the new degree of freedom to curvature in more non-trivial ways. Now, the complementary information that we can extract from different observations come from, for example, gravitational waves at any scale, as I advertised earlier, and fifth force effects at local scales. Now, what this means is that usually the new degrees of freedom we introduce to explain the acceleration leave a residual force at local scales, with modulo various screening mechanisms, they leave some observational imprint, which we can constrain and then try to relate with the theory, the properties of the theory at large scales. Now, I'm going to introduce what has been dubbed in the literature the dark degeneracy, and it's a very simple, extremely simple statement, which is important to point out before building up model-independent tests. This is the fact that, probably the obvious fact, that the Einstein equations are telling us that geometry responds to the total energy momentum content in the universe. What this means is that gravitational probes by themselves are unable to distinguish to tell us to give us information about the particular properties of either dark energy or dark matter, at least with our current knowledge of the dark sector. This is important because, as I'm going to argue, what one can do at best in a model-independent way is to indeed reconstruct the left-hand side and forget about mapping geometry to the individual components of the right-hand side of the Einstein equations. So this is another side of an old problem. For example, when we're trying to measure the mass of a star or the sun, we don't measure the mass directly. Well, what we measure is G times m, the Newton's constant times the mass. And in order to extract the mass, we have to make some assumptions about the gravitational coupling, which is pretty poorly measured coupling, in fact. So for any meaningful discussion on distinguishing dark matter from dark energy, we need to have a well-working definition of what I meant to say distinction between the modified gravity and dark energy. We need to define what we mean by modified gravity. We need to have a consistent definition of it, which here I'm going to define as any theory that modifies what is the genuine degree of freedom of general relativity, and this is the graviton. So different theories, at least in the way I introduced them earlier, modify the propagation of tensors in different ways. For example, Hordensky theories, the general scalar tensor theories introduce a running of the Planck mass, because the Planck mass is played by a dynamical degree of freedom here, and they introduce an extra friction term, and they also modify the speed of tensors. This is because the light cone structure of gravitons is changed compared to that of photons due to the non-trivial interaction, derivative interactions between the scalar and the metric. Now, Einstein ether theories, for example, vector theories, in principle changes the propagation speed, while biometric theories introduce a mass to the graviton and a source coming from the second tensor field. So, armed with that, I'm going to question now what we actually observe. Since dark matter and dark energy are unobservable, what do we really observe on the sky? So as Leonardo Senatore was pointing out in his talk, what we observe is light along our past light cone. We are interested in light coming from galaxies. And galaxies in cosmology are our test particles. They probe the underlying gravitational field. And I'm going to assume here that the galaxies move along geodesics. This assumption is going to eliminate any ambiguity about the choice of conformal frame, for example, Jordan-Einstein frame. So I'm going to fix my frame to be, the physical frame to be the one where galaxies move along geodesics. And now, so looking at galaxies, we can map out the distribution on the sky, and from that we can extract the cluster, the strength of clustering. And of course, galaxies are biased tracers of the underlying gravitational field, and part of it is produced by dark matter over densities. So we can try to map it out to extract information about the dark matter clustering, but in a model-independent way, without assuming any particular model. The bias function is in principle unknown. At the same time, if we assume that the equivalence principle holds, so galaxies fall under the same rate with dark matter, so the velocity field or the acceleration field, if you like, of the galaxies is equals to that of dark matter. So linear perturbation theory around FRW is telling us that we can relate it to the time derivative of the dark matter density field. However, again, this is in principle unknown. This is in principle unknown without the assumption of any particular model, because we need to set up an initial condition sufficiently early in the cosmological evolution. So the takeaway message here is that whenever we try to go from the left, from this box to the right one, we are facing the problem of having to define a particular model. So just to make the discussion a little bit more precise, I'm going to assume scalar fluctuations around Friedmann-Robinson-Walker, parameterized by these two potentials, phi and psi. So these are small potentials, just small perturbations, and matter reacts as usual to psi through the Poisson equation. I have decided to factor it out this way, so G times delta rho total as equals some G effective times delta rho dark matter, just to highlight the fact that by looking at the G effective, at trying to constrain G effective by itself, it's not going to tell us necessarily some information about modified gravity, because we might be dealing with some dark energy component which clusters, and this might manifest itself as a change in the gravitational strength at large scales. However, at late times, we can do something which is better. At late times, we can neglect the free streaming of neutrinos, which introduce a source of anisotropic stress. And then the anisotropy equation relates the difference between the two potentials. If we are dealing with, in the presence of a perfect fluid, the right-hand side is going to be sourced. The only source that remains on the right, the only possibility for a source on the right-hand side is some modification of gravity. So modified gravity models essentially introduce an anisotropy in the effective fluid at large scales, and this manifests itself as a gravitational slip. So the potentials are not equal to each other. So the gravitational slip essentially is a key discriminator between modified gravity and GR, or theories, dark energy theories that do not mess with the law of gravity. And in fact, we can reconstruct it in a way that is model independent. So what I'm going to argue now is that we can forget about trying to map out the observations to the individual properties of dark matter, of the dark sector, if you like, and try to reconstruct geometry instead. So if galaxies move on geodesics, then we can write down a geodesic equation for them. The galactic velocity field is unobservable. We also observe weak lensing, which is a measurement of the combination of the two potentials phi and psi. So the galactic velocity field essentially measures psi, and we can combine these two to build an expression for the gravitational slip, which depends only on observable quantities that depend on the velocity field of galaxies and the lensing potential. Now, any observation of eta departing from 1 is going to be the smoking gun of modified gravity at late times. So eta equals to 1 in lambda CDM, quintessence, k-essence model, but it's not equal to 1 in the old F of R theories, Hordensky, bimetric, Einstein, ether. So I'm going to now demonstrate, try to convince you that there is a link between the gravitational slip and the propagation of tensors at any scale. So the statement would go as follows, that for the general modified gravity models I introduced earlier, the theory parameters controlling the linear anisotropic stress, or the existence of the gravitational slip, are exactly those that modify the propagation of gravitational waves at any scale. So in the way I explained earlier, we can have a modification in the friction term, the speed or the mass of graviton, or some source due to the presence of an extra tensor field. And these are the parameters which are going to control the amplitude of what source is, the amplitude of anisotropic stress. So physically what this means is that we have a bridge, phenomenological bridge between tensor and scalar fluctuations. If we have a measurement, as we do, about this sector, we can try and go back and make a statement about the properties of the theory of the properties of scalar fluctuations at linear scales. And this is what I'm going to explain in a bit using the recent gravitational wave observations. So let me give you an example about this link, an example from the past, because the Hordensky theory is to a big extent ruled out recently. So let me introduce it very briefly. So the Hordensky theory starts with the k-essence term, the so-called kinetic gravity braiding term, a term that couples the scalar to the curvature in a conformal way, and non-trivial kinetic derivative interactions between the scalar and gravity. Essentially, it is these interactions here that change the speed of tensors. And these are the operators that have been recently ruled out. So here we have the running of the Planck mass, the change in the speed of tensors parameterized by this parameter alpha t, which is called tensor speed excess. It measures how much we deviate from the speed of light. And anisotropic stress is related to exactly the same two parameters that modify the propagation of tensors. Now, for the case of Einstein ether, we have a similar situation. So if we start from the Lagrangian and we think of the gradient of the vector, if we would decompose the gradient of the vector in a kinematic decomposition, the coefficient of the shear will be given by beta 1 and beta 3. So these are constant theory parameters. And these are what this combination, the combination of the shear that appears in the combination, of anisotropic stress that appears in the anisotropic equation, and the one that modifies the speed of tensors. So this is a very simple link, pretty simple, which can have some interesting phenomenological implications, which I will get back very shortly. So let me now ask the opposite question. So let's assume that, we know that gravitational slip it means that gravity, the existence of gravitational slip modifies gravity. Means that gravity is modified. Does the opposite hold true? So can we imagine that we can be dealing with a situation where there is no gravitational slip, but gravity is still modified? Or to put it differently, can we have a modified gravity theory that conspires in such a way to mimic GR at large scales? And this is, from a phenomenological point of view, this makes sense to ask, because let's assume that Euclid in the future measures it, that there is no gravitational slip. How sure can we be that this is not a modification of gravity? Okay, so it turns out that we cannot have it, and what we did here to study to start for the models I talked about earlier, to investigate whether setting the anisotropic stress equal to 0 at some initial time and scale in the cosmological evolution, and ask whether this condition is preserved under time evolution of the system. So thus, if we assume that the model can mimics GR at some initial time and scale, is this initial condition preserved under time evolution along the equations of motion of the system, which is what this symbol here means? And leaving aside the technical details, what it turns out is that for biometric gravity, there is no dynamical screening or shielding, if you like, at large scales. So we cannot have this situation. So for Einstein ether and Hordensky theories, this could happen, but it corresponds to either extremely fine-tuned initial conditions or singular evolution. For example, for Hordensky, this means that we are running into strongly coupled configurations, or the scalar decouples completely from the dynamics. So the takeaway message here is that it seems highly unlikely that we can have a modified gravity theory which mimics GR at large scales, which can mimic GR at large scales, at least in the way I introduced it earlier, but through the generation of gravitational slip. Can I ask how much time do I have? Fantastic, thank you. Now, the recent gravitational wave observations measured the speed of tensors, and essentially their speed is for practical purposes equal to that of light. And what I'm going to do now is use this link between tensors and scalar fluctuations and do the reverse engineering and make a statement about the phenomenology of these models, at the cosmological phenomenology of these models at large scales. So for the Hordensky theory, what remains is essentially just these three terms. So anything essentially up to that couples the scalar up to Brans-Dicke type of coupling, the rest are gone. So beyond Hordensky, theories have been also constrained through a particular requirement for the relevant operators Einstein theories can give speed of tensors equal to 1, provided essentially the parameters controlling the anisotropic stress give us 0. And something similar happens for Proca theories. So to summarize the resulting phenomenological implications, I would say the following. For the remaining scalar tensor theories and vector tensor theories, the linear clustering of matter can only be made stronger than GR. This means that the G effective at large scales is greater than 1. So this constraint, the measurement of the speed of tensors, is constraining, implies that the clustering of matter can only be made stronger than GR at large scales. So the gravitational slip can be only produced by conformally coupled scalar tensor sector, and any detection of it would essentially rule out vector tensor theories. Biometric theories can have eta equal different to 1 and G effective less than 1. However, the cosmological evolution has been shown to be pathological, so I'm not going to consider them anymore. And essentially, to be a little more precise, so if the remaining scalar tensor sector is telling us that Ricci scalar, so the Ricci scalar coupled, non-minimal coupled to the scalar field, so essentially Brans-Dicke coupling plus the K essence term predicts that eta, the parameter eta is always less or equal than 1. If we have this extra remaining operator, the so-called KGB term, eta can be made either larger or less, and vector theories predict always eta equal to 1. Now, the lensing is going to be different than 1 for these theories, simply because this term modifies it. So the other two models are allowed to couple the extra degree of freedom to curvature only in a conformal way, and as such, they don't modify lensing. So we can build these consistency conditions which are telling us that if we measure within some statistical significance this for eta and sigma, we are dealing with a conformally coupled scalar, and if any violation of these two will signal the presence of kinetic gravity braiding. And of course, any detection of eta equal to 1 would be telling us something about the vectors. So now I'm going to switch gears, and I'm going to talk about astrophysics. So there has been a second important aftermath of the measurement of the speed of gravitational waves, and this is the fact that the screening mechanism within matter sources, such as stars, for general scalar tensor theories, is not effectively operating anymore. This means that the gravitational force is modified through a fifth force term in the Poisson equation, which is going to depend on the density and its first derivative, the stellar density and its first derivative, and its overall coupling strength depends on a dimensionless parameter we call y here. What is important here is that y relates to the properties of the theory parameters at large scale. So any constraint on y can translate to constraints on the theory at large scales. So what I'm going to argue now is how we can place a new constraint on y looking at white dwarf stars. So let me just very briefly introduce what white dwarfs are, at least some very important points for this analysis. So white dwarfs are very old stars. They have exhausted all their fuel, and they're supported by the pressure of the degenerate electrons in their core. So this is essentially the old Chandrasekhar model, the Chandrasekhar equation of state, which describes the pressure in the white dwarf core as a degenerate Fermi gas. What is important here is that if we want to go beyond, if we want to derive precise, if we want to build precision tests for gravity, and with the particular data we'll be using here, the precision of the particular data, we need to go beyond this. We need to go beyond this model. The first correction comes at zero temperature, and this has to do with the fact that electrons are not alone in the core of the star. They interact with the positive ions through electrostatic interactions. And this has the effect of reducing about 4 to 5% the radius you would calculate by using the standard Chandrasekhar model. Most importantly, we have residual effects coming from the thermal history of the star, for example, temperature, the envelope structure of the star. And all these essentially are a result of the evolution of the star and down to up to the point where we observe them. And what is important, it's important to point out here that previous studies of modified gravity with white dwarfs have been based essentially on, at most on the Chandrasekhar model. But it turns out that neglecting these residual effects from the star's evolution history is very important. And let me show you why. So these are the data we are using. They are data from stars in binaries. This is very important because the mass and radius is measured independently here. And that's because we are trying to measure the mass-radius relation, and we don't want to have any bias coming from any underlying assumption about the mass-radius itself. So actually, it makes perfect sense here that a weaker gravity is going to make the star larger at fixed mass, which corresponds to positive y, and y is the parameter I introduced earlier through the Poisson equation. It's the coupling, the coupling strength of the fifth force, of the new fifth force. And these are different mass-radius relations constructed at assuming the most general equation of state at zero temperature, also known as the Hamada-Salpeter equation of state. So this is the important plot that I would like to show you here, and this is what we get if we do the statistical analysis in constraining y by using this sample. So these are the contours, the 2 sigma contours of y each star prefers. R here stands for the observed radius. And hotter stars tend to, the temperature of the stars tends to increase along the vertical axis. So this is a clear detection of modified gravity. Okay, y equals 0 corresponds to Newtonian gravity, but you can see that stars tend to, larger stars or hotter stars, if you like, tend to prefer weaker and weaker gravity in their interior. But this is wrong. This is completely wrong. There's nothing wrong with the statistics. What is wrong is with our assumptions. We've modeled the stars at zero temperature, and this introduces a very crucial systematic. So what happens here is that gravity, the weakening of gravity comes to substitute the effect of temperature. And this introduces a very important systematic in our results. And this is in clear contradiction with the fact that y is assumed to be a global parameter. Because, as you can see, each star, or at least different subgroups of stars, tend to prefer their own value of y. So we cannot do statistics with this sample because the data are clearly in tension. And this is because we missed to model the envelope and temperature effects. So this made us think. We modeled, we added corrections coming from temperature and envelope structure. So we added an envelope around the core of the star that we computed within modified gravity. And then, of course, we used 2 sets of simulations, stellar evolution simulations, that were available to us for 2 types of envelopes, thin envelopes and thick envelopes. And thickness here means essentially the mass fraction of the envelope. The simulations were done in Newtonian gravity, so we assume that we can just, as a first approximation, add them on top of the modified gravity simulations that we had. So as a general trend, the contours tend to be pushed down, which is good. And what happens is that still the data seem to be incompatible, the contours seem to be incompatible with Newtonian gravity. However, the picture has now changed quite a lot, and particularly for thicker envelopes, we get something that is much more consistent. What happens now is that essentially different envelope structures introduce different constraints. So essentially, the way one could interpret this is that how well does the modeling of the star, the envelope and temperature modeling of the star fits with the modification of gravity. So what is important here is that we can indeed extract a very robust and unambiguous bound for the coupling y, which improves up to a factor of 3 compared to the previous one. And this is by looking already at the coldest star in our sample. Since temperature and gravity, weakening of gravity, have the same effect, so the coldest star already places a bound, an upper bound on the modification on the fifth force coupling y. Now, this constraint has been translated to constraints on the effective theory at large scales. And the question is whether we can do. Sorry, Patrick, do I have about 5 minutes? 5 minutes. Okay, excellent. Thank you. So, so I just wanted to say from before that essentially these constraints here can be interpreted as constraints on the thickness, how much the thickness of the surrounding envelope could be given the modification of gravity. And instead we can ask whether we can do something better in terms of constraining our theory. Either this theory, this particular theory I talked about, which is the remaining, it's part of the remaining scalar tensor sector of general scalar tensor theories, or other theories similar to that, theories that predict the modification of gravity in stellar interiors. And the answer is that the future can be very, one can be very optimistic for the future, and something we are looking at the moment is the physics of stellar pulsations. So what are stellar pulsations? So stars are not static. They pulsate around their equilibrium structure, around their equilibrium configuration. And these tiny fluctuations essentially manifest themselves as tiny variations in their luminosity. Now, traditionally, this has been a test on the assumptions on the star's chemical makeup, the microphysics of the star, through inversion techniques. For example, the physics of convection, opacity, nuclear physics, and so on. And the idea is to use it as a probe of gravity in the stellar interior. Now, what is key about seismology is the fact that different modes, different pulsation modes, probe different parts of the star. So they provide us information about the microphysics or gravity at different part of the star. For example, modes, these modes shown here is modes of high degree, like this one, are pretty shallow. The probe regions very close to the surface, while other ones are more penetrative towards the star's core. And the idea is to use, in particular, helioseismology, which is the study of solar pulsations. So the sun exhibits pulsations of acoustic nature. So these are pulsations driven by, supported by pressure in the stellar interior. And the actual accuracy is extremely good. It's about the observed frequencies are observed to 1 in 10 to the 5. So the star is, the sun is not a typical object that you would think as that you would use to test gravity, but essentially the accuracy compensates for that. For what I'm showing you here is a typical result, standard result from heliosismology, which is the reconstruction of the speed of sound in its interior. So the idea is that one assumes a reference model in the background, which has a certain prediction for the speed of sound, so that then by looking at the different modes and the parts that they constrain, the difference between the reference model and the observed frequencies are telling us something about the correction to the speed of sound at this part of the star. So this reconstruction of the speed of sound in the stellar solar interior has been one of the great successes of heliosismology, and the idea is to use it as to test, I'm almost done, to test the theory I introduced earlier. So I'm not showing you any actual result, but it seems that one can improve on the bounds for y, at least with our current results, which I would not quote with big certainty, but one can improve about 2 orders of magnitude, which is a very good improvement, and the physics is, I think it's a very interesting path to explore. So I'm going to leave you with my summary, which is essentially the importance of building model-independent observables, in particular observables that are able to discriminate amongst different classes, general classes of gravity models. It is essentially the gravitational slip. The gravitational slip links with gravitational waves, and this allows us to do the reverse engineering and make predictions about to connect tensors with scalars. And the breaking of the screening mechanism within stellar interiors that came after the recent measurement of the speed of tensors gives us a very great opportunity to test gravity at local scales. Now, a takeaway message here is that one has to mind the subtle astrophysics in the star and think also about more accurate and precision tests. Okay, thank you a lot.